Yeah, so the result is, it's a very short title, fully acronymed. ETH implies PIH. So ETH is exponential time hypothesis. I'll define it, which probably many of you know also. And PIH is basically like the analog of the PCP theorem in the world of parameterized complexity, if you want to state it loosely. But it's basically says that a basic problem in parameterized complexity is hard to approximate rather than just hard to solve exactly. And that is still, and we would like to give good complexity theoretic evidence for that. And this work says that you can actually prove that under ETH, which is a widely believed assumption. Okay. So, and this is a recent paper which we just finished. It's up on ECCC and archive, and it's joint work with Xuan Diren, who's my PhD student, and the collaborators Ikanson, Kevin Wu, who's also a PhD student at Berkeley, and Bing Kai Lin. Okay. Again, I sort of only loosely planned this talk. So if you have any questions, and it's on the board, so just ask, and it should be good. We can figure it out. Okay, so I want to start by, as I said, maybe I'll start just very, just to warm up, I'll define what ETH is. So that please get that out of the way. So ETH is exponential time hypothesis, and if I want to just basically say the simplest form, I can just say that there exists a delta greater than 0 such that, let's say, 3-SAT requires 2 to the delta n time, where n is the number of variables. That's it. Right, so the fastest known algorithms for 3-SAT are all exponential. I forget what is the current record, probably like 1.31 to the n. But many of you probably have seen Schoning's beautiful 4/3 to the n algorithm and so on. But the point is all of them are the form 2 to the sum alpha times n. And this says that you can't have a 2 to the little o of n algorithm. Okay, so that is ETH. And so it's also, so this fact is not, so it's also known. So actually, let me just leave it at this. I was going to say that you can assume the same thing also under the assumption of bounded occurrence 3-SAT. So you can take 3-SAT formula which have each variable occurs only in a few clauses. And ETH implies that that problem is also exponentially hard using, and this is not that easy to prove, but this is based on this sparsification lemma and so on. And I'm just mentioning that because for many of the reductions in parameterized and fine-grained hardness, it's very nice to have that bounded occurrence thing. So that will come up later maybe, so I'll just throw it. But this is ETH, and I'm going to define what PIH is. And for that, I want to start by the regular PCP thing, which is probably much more familiar thing. So PCP theorem, and I'm going to state it as a hardness of approximation of CSP. CSP is constraint satisfaction problem. So I'll define what it is in a second. So there are many ways to state this. I'm going to state the PCP theorem as the hardness approximation of some SAT-like problem. So one way to actually state PCP theorem would be to say that if I give you a 3-SAT formula and I ask you, tell me if it is satisfiable or if any assignment will fail to satisfy 1% of the constraints. Telling these two apart is NP hard. That's what the PCP theorem says. Okay, and so that is for 3-variable thing, but you can bring down the arity, which is the number of variables each constraint depends on, to 2. So what is a 2 CSP? So I'm going to state it for 2 CSP because that connects to things like clique and so on. So what is a 2 CSP? So an instance consists of just a graph G, V, E, and along with a relation, let's say pi E, okay, so there is that. There is an alphabet sigma where the variable should take values, and then there is a relation pi E for all E. Okay, so it's really the picture is that you have a graph, and there are some edges, and for each edge there is a relation pi E1, pi E2, and so on, and it's just a relation on sigma. And what is your goal? Goal is to find an assignment sigma from V to sigma such that or maximizing the fraction of edges such that you can imagine what it will be. So the two values given belong to the relation. So sigma u, sigma v is in pi. Okay, so this is, in general, this can also be a directed graph, but here the relation is directed. So, but you can just pick some canonical ordering between u and v and have this. And you can have multiple things. You can have loops if you want. You can have parallel relations and all that, but let's not worry about those things. Let's just keep with this. Okay, and so this is the thing. And then the PCP theorem says, and let's say that this is so the opt of an instance psi. So let's call this instance to be psi. An opt of an instance psi is really the maximum over all assignments of the value of the assignment. So this fraction, let's call this optimal fraction to be for any sigma, let's say the fraction of edges it satisfies to be its value, and you want to maximize the value. Okay? So that is the optimum value. And the PCP theorem says, given 2 CSP instance psi, it's NP hard to tell if between the two cases, yes case, opt of psi is 1, and the no case, opt of psi is less than rho. Okay, less than or equal to rho. Well, yeah, so I should have said, so there exists some absolute constant rho less than 1 such that this is true. Okay, so I should have said that.
So at sigma 0, 1, this is just max 2.
Yeah, so when sigma is 0, 1, actually this problem, you don't have, this doesn't say anything. Okay, so again, I've been very bad with quantifiers. Really, I should have said there exists rho less than 1 and there exists sigma. Such that, a finite sigma. Okay, sorry to really mess this up here. Maybe I'll rewrite that. So, because when sigma is 2, actually, this problem, this cannot hold because I'm also demanding perfect completeness. So, but sigma can be anything, and in fact, I'm going to give an example here. So this is the PCP theorem. So sigma can be anything. So the thing is that in 3-sat, it's really not important to insist that this is 2. It's just convenient, and 2 suffices. And the nice thing is then you can visualize things as graphs, right, rather than hypergraphs. But the thing you have to give up is that sigma has to be big. But it turns out in parameterized world, sigma is anyway going to be the growing parameter. So it sort of fits that mold very well. And a very easy example would be to take sigma to be 0, 1, 2. Right? And you can ask what is, and this, in this case, what you really, and then pi e can be the not equal. And then you get max 3 coloring. So given a graph, can you 3 color it so that it's perfectly colored, or must every 3 coloring get some constant fraction of edges monochromatic? That is NP hard. Okay, that's what the PCP theorem proves for us. Okay. Right, so that's the PCP theorem. And in fact, so this shows that in fact you can take sigma to be 3, size 3. And the rho, of course, it depends on, there are tighter forms of PCP theorems which try to optimize rho and so on. For us, in this talk, any rho bounded away from 1 is good enough. For example, I started with 3-sat, so it is a famous theorem of Hastad's that given a 3-sat instance, telling if opt is 1, so it is satisfiable, versus opt is at most 7/8 plus epsilon, is NP hard. And 7/8 is significant because if you take a 3-sat thing where every clause has 3 literals, just if you take a random assignment, in expectation, you will satisfy 7/8 of the clauses. So 7/8 is basically trivial to achieve without even looking at the instance. You can just pick a random assignment. And Hastad's result says that that's the best you can get. So there are such tight hardness of approximation results, also known for specific templates and so on. Okay? But here I'll just leave it vague, so I allow you to put any relation you want, constraining pairs of variables. Okay? And note that importantly here, what is growing is that size of V is growing, sigma is fixed. Okay, that's the setting. And that's going, we are just basically going to flip it, and we're going to get parameterized CSP. Okay, so any questions so far? Again, really treat this as like a course lecture or something, so just stop me anytime, okay? So
what happens when sigma equals 2?
yeah, when sigma equals 2, you can get the same thing, but you won't get a 2 CSP, you need to have a 3 CSP. So the constraints will depend on 3 or more variables. You can do that, or instead of insisting this is 1, you can say this is 0.9 and this is 0.8, and then also you can get hardness. Only reason 2 doesn't work is that 2 sat is an easy problem. So if you have arity 2 over Boolean, you can decide it. Okay, so of course then it's not NP hard. But 3, immediately you get max 3 coloring, this is hard. Okay, so parameterized. Again, I'll stick with 2 CSP, but really it's not so important. So one thing maybe I'll mention that. So the point is, once you get any, okay, maybe I'll just say this, get PCP for any finite sigma, that implies PCP, or not this, sorry, for any arity, arity 2. So I'll just throw this in as well. So if you got, instead of 2 CSP, if you got 1000 CSP, where the constraints depends on 1000 things, you can convert it to 2 CSP, but the price you'll pay is the alphabet size. Okay, so there are some standard transformations. So that's why when you think of PCP theorem, often you think about a verifier who makes a constant number of queries and so on.
This is the label cover.
This is like the label cover type there. Yeah. Okay. So maybe I'll actually come back to that. Maybe let me define parameterized 2 CSP, state PIH, so at least we know what we're talking about. Then I'll come to how do you prove this PCP theorem. Right? The PCP is probabilistically checkable proof. It doesn't say anything about CSP, etc. So you actually think about a verifier writing down a proof and you checking it with few queries and so on. You might have seen that view. And that's operationally the convenient view for us also. So I'll mention that shortly. But let's talk about parameterized 2 CSP. So it's really the same thing. So 2 CSP with the parameter. Now, in a parameterized problem, I just have to give you one more input parameter. What is the parameter? With the size of the vertex set as parameter. So really what I'm going to think about here is that the size of V is, because this is a generic problem, right? So typically you think of a big graph and 3 colors. But you can think of a small graph and getting lots of values. And I'll show a very natural problem that way. So this is a parameter, right? And then the size of sigma is growing. That is the input size. Okay, so that is parameterized 2 CSP. So now the following is a well-known fact. So classic theorem. For parameterized 2 CSP, telling if it is satisfiable, namely if opt is 1, that is W1 hard. Okay? And it's not too important what W1 hard is, but it basically means that, so unlikely to be in FPT, so and I'll say what that is in a second. So it's unlikely to be fixed parameter tractable. So what do I mean by that? If you give me a 2 CSP instance like this, there is a simple brute force algorithm for it. Namely, brute force over all assignments to the variables. Now, if sigma is size n and there are k variables, there are only n to the k assignments. Right? So there is a trivial n to the k time algorithm to decide parameterized CSP. So unlikely to be in FPT means that no f of k n to the c algorithm for some fixed c. Okay? And this f can be anything you want. So this is the standard way you talk about parameterized thing. Any exponential dependence is restricted to the parameter. Whereas here, this is k is it's n to the k. So you want to avoid that. You want to have f of k. You don't want the running time to grow in the exponent with k. Okay. So that's the classic theorem. And so I'll state what, let's see what I want to do first. Maybe I'll do any questions so far? And I'll give you an example of this problem, very nice example called, basically, you all probably know the k-clique problem is one of the classic things, which is W1 complete, but I'll only worry about hardness. So this is k-clique is W1 hard. And what is k-clique? So you're given a graph G on n vertices. And you want to know, is there a clique of size k? Okay. And again, there's a trivial n to the k algorithm or n choose k algorithm, right? Just brute force all the k size sets and check this thing. And the W1 hardness says that it's unlikely to have, for example, a 2 to the k times n square algorithm. Okay, and that's a very standard result in parameterized complexity. And now turns out you can really think of this 2CSP very closely. Clique is essentially this 2CSP is k-clique. Well, not exactly k-clique, but something called the multicolored k-clique. I just want to do this so that, clique is a very nice problem. So I want you to have some sort of nice mental image of this CSP. So what is multicolored k-clique? I'm going to give you a graph, but now its vertices are going to be partitioned into k parts, V1 to Vk. And you're asking, is there a clique which picks one vertex from each of these? Okay, so is there a clique with one vertex from each Vi? And the graph, you're given the graph with the partition. Okay? So G is basically V1 disjoint union, V2 summates. You can have edges all over. Yeah, so it doesn't have to be. And of course, you can force this by just making the VI's independent set. So then if you have a k-clique, it must really have one per VI. So it's really, I'm basically giving you a graph which is k colorable, and I give you the k coloring, and I ask you, can you prove that it cannot be colored with less than k colors, because there is a k-clique. Okay. So this is also, so multicolored k-clique is also W1 all. And there is a very simple reduction from k-clique to multicolored k-clique just by duplicating things and so on. But now I want to say that multicolored k-clique is exactly 2CSP. Okay, so note and with a parameter being k. Okay? So really, when you think of 2CSP, it looks all abstract and all this, but you can just have this picture in mind. You have some blobs. You have to pick one vertex from each blob, and you want to know, can you get a clique? And why is that? Well, you really okay, so it's not exactly equal, I guess. Let me put a squiggly. So the reason is that if all the VI's are equal, in fact, it's exactly equal when, actually, even otherwise, you can do some padding, I guess. So I'll actually say this. It's actually equal. So why is that? You really just make each of these VI's equal to sigma. So think of these k blocks as k variables. And picking one of those things is assigning it a value. If you make all of these equal to sigma, picking a point in each is assigning it a value. And what are the relations? Well, the relations, if I want the relation between two variables, I just look at the bipartite graph between them. That's my relation. Right? And so my goal is to just pick one variable to maximize the number of edges I get. The biggest it could be is clique. And that's exactly 2CSP. Okay? Okay, that's all good. Now, the thing is, this is W1 hard, but this only talks about exactly satisfying it. What about approximation? Suppose I give you or let's talk in terms of this. So approximate 2CSP, parameterized 2CSP, And that's actually going to be equal to, I'll just mention this, though I'll maybe stick with this view for the talk. It's going to be multicolored densest K subgraph. So another classic problem, how do you pick K vertices in a graph so that maybe you don't get a clique, but you want to pick as many edges inside that set as you can. And that problem is well defined. That is the problem. That is the 2CSP problem where you have, it may not be satisfiable. And that's what this approximate parameterized 2CSP is. So what's the PIH? What's the, so I'll now finally say the other part of the talk, parameterized inapproximability hypothesis. Which is PIH. And that basically says that there is some constant. So basically, it says this. In the parameterized world, it says that, so I'm going to state it in this way. So there is no FPT algorithm. I'll state it this way because it's a hypothesis. So it says there is no algorithm rather than, sometimes it's stated as this problem is W1 hard, but I want to state it this way so that I can then actually say it's implied by some other hardness assumption. There is no FPT algorithm that can distinguish, again, there exists rho less than 1 such that there is no FPT algorithm that can distinguish param 2 CSP instance if param 2 CSP instance psi has opt psi equals 1 or opt psi. Okay? Literally exactly the same thing. But now instead of saying there is no polynomial time algorithm, you say there is no fixed parameter tractable algorithm. And in particular, what that will, for example, say here is that if I give you, again, if you like graphs, right, I give you a graph, this multicolored version or k-partite version. Multicolored is just k-partite. Right? It's hard to tell if there is actually a k-clique or if any k vertices you pick is going to miss at least, say, 1% of the edges inside that. Okay? So that's the version. So this is the parameterized.
So the equivalent of PCP would be that there is no such thing unless W1.
Yes. Okay. Excellent. So that's why when I always swallow a little bit when I say this is what we do is the analog of the PCP theorem, because the true analog of the PCP theorem would be to say that distinguishing this is W1 hard. And that I would view as the PCP theorem in the parameterized world. And that's really still, I mean, that's been an open question for a while. People have been really, I mean, it has emerged as one of the sort of pesky open questions. But we don't, unfortunately, actually fully solve that. But I guess we get somewhat close because we get it from an assumption like ETH. Okay, and now our theorem is clear.
So ETH is stronger than W1.
Yes, ETH is stronger than, and those are very simple reductions. And I'll mention a little bit about that too next. Okay, so that's the story. Yeah. So the conjecture really, so you could say that, okay, so again so true analog of PCP would be that the above problem is W1 hard, as Arvind says. Okay, we don't say that, we basically get something, or another way to say it is that W1 not equal FPT, which implies PIH. So that would be a nice theorem. But this is a weaker assumption. ETH implies this. So we are actually saying this implies this. So if you show this, you'll be done. But we are basically only proving this implication. And there is actually some even wilder, very strong assumption called gap ETH, which of course implies ETH. And then it was known that that implies PIH. Okay? But that's a little bit of cheating because you're making such a strong assumption that in particular there's a gap in your assumption. So the nice thing about this result is that ETH is a worst case assumption still. Sure, it's a very strong assumption, much stronger than P not equal to NP, etc. But it still is assumption about exact satisfiability, and you're creating this gap, which is in some sense the essence of PCP theorem and so on. So in that sense, our work fits the spirit of PCP theorem, though technically it doesn't quite match what we would like. All right. Okay, so maybe one thing I'll mention is there was, so for this K-clique problem, so one of the fallouts, early fallouts of the PCP theorem was, in fact, it was one of the driving forces and motivators, was to show hardness of approximating clique, right? The first FGLSS paper and so on. And here also, if you want, you can ask also for K-clique, I give you a graph, is there a K-clique, or does every clique have size less than K by 2? What is its complexity? Could it be in FPT? And now if you prove the PIH, that implies that, again, by standard FGLSS type reduction, that problem is also hard. But actually for clique, so the following, so Binkai Lin in a couple of years ago, I guess it was, when was it? 21, I guess, yeah. So he showed that telling if omega g is at least k or omega g is at most k by 2, I just picked this, you can actually make this any constant by just tensoring, is W1 hard. So one of the, so this is actually was very surprising because he was able to do this without proving the PIH. There was somehow a general feeling that maybe you need to prove PIH to do this, but turns out this is was simpler to do because the gap is in sort of, getting a full clique is much more power than just getting many edges satisfied wherever they might be. Okay, so I just want to mention that this is a very nice, beautiful result. And there have been some follow-ups which have further simplified Lin's result and also got much bigger gaps. Even by this point, I think the gap is like k to the 1 minus little of 1 or something, at least some k to some power. So you can put some k to the 0.1 here, I think.
Because clique is much harder to approximate than.
Yeah, somehow when you have a clique, you have a set where every constraint is satisfied inside it. So from that, you can get something where every constraint is satisfied. It's, yeah. Somehow it just gives you a little bit more power. And actually, in the PCP world, there is a reverse connection saying very strong hardness for clique at the right gap location implies some PCP.
So this theorem avoids the PCP.
Yeah, this theorem avoids the PCP. I mean, it has very PCP-like ingredients. It's based on Hadamard code and all those things. But somehow in the analysis, the fact that you get a clique lets them bypass things. And also the fact that the reduction can be parameterized also makes it easy. So you can have a reduction running in 2 to the k time, for example. That gives a little more power in this. And in fact, that's true. I should also say that, I mean, obviously, I won't do too much of the details of the proof, but if I had, say, if all this was set up and I have to do the proof, I can do most details in, a 90-minute lecture, for example. So this proof is actually quite self-contained because in one sense, it seemed harder to do this in the parameterized world, but in hindsight, it was a little bit easier because we can make the reduction run in FPT time. It doesn't have to be poly time. And that gives you some extra wings to do things. Okay, so let me see what do I want to say next. Okay, so maybe I'll just quickly say this gap ETH to this thing. Maybe it's instructive to see a little bit of that. And then I'll say a little bit about how we get things. I'll talk a little bit about PCP also, because I was told that many students here have seen the PCP theorem statement, but maybe not ingredients of its proof. So I'll just focus on one aspect of how you prove it, which is really what we build on. I'll spend some time on that, and then I'll say what we do different for this. But maybe I'll quickly sketch just at least the reduction to see what is this connection between ETH and this at some high level. So how can you do this? So gap ETH will basically say the following. There exists a rho less than 1 and delta greater than 0, such that even approximating 3 sat requires 2 to the delta n time. Okay? And by standard things, I will use the coloring thing. So it basically says that there exists some epsilon delta greater than 0, such that 3 coloring. So following needs, sorry, I'm writing too small here, 2 to the delta n time. So 1, G is 3 colorable. I'll just work with this because the arity is 2. It's a little bit nicer. And by standard reductions, sparsification, this holds. And every 3 coloring miscolors epsilon fraction of edges. Okay, so this is basically, the PCP theorem tells us that this is NP hard, but this is some souped up assumption. We say that this actually requires exponential time. So if we have this, and the gap ETH implies, you can even say this as the statement of gap ETH if you wish. Okay, take it as a definition. And now, how do you prove PIH from this? And again, I should say this whole work is just a reduction. We're reducing some problem, which we believe takes exponential time, to some 2 CSP, such that if there is an FPT algorithm for to the 2 CSP, you will get a sub-exponential algorithm, which is not there. Okay? And the reduction uses PCP type things, like Hadamard code, verification, and so on, but ultimately it is a reduction. Here it's actually a very simple reduction. So how would sort of the reduction go? So you make k variables. You can think of it as a multicolored clay cake also. But let's, wondering if that's the best way to. Yeah, maybe you can, let's think about that picture. So you have k variables or k parts, v1, v2 to vk. Right? So these are just, each of these is n over k vertices. So you write v as v1 disjoint union vk. Each vi is of size n over k, where n is the number of vertices. I'm reducing this problem to PIH or this 2 CSP or this multicolored k clique. So I do this, and what is sigma going to be? For this n over k variables, what are all the possible colorings? Right? There are 3 to the n over k colorings. Actually, you can make it a little bit smaller. You can just take all legal colorings, but let's just take all colorings. And if it's not legal, it will be an isolated vertex. It will be useless. So all colorings of this. So this sigma is all 3 colorings of n over k vertices. Okay? And now, so there won't be any edge inside each part. How will I put an edge between 2 things? I'll put an edge between 2 things if the union of those, if these coloring and this coloring doesn't miscolor anything. Okay, so again, I'm not writing that. So you put an edge between, so this is some coloring chi to V1. This is some coloring chi to V2. If this coloring together with this coloring, which are on disjoint vertices, doesn't get any violated edge, then you put an edge. Okay? And note that you can do this entire reduction in some 2 to the n over k type time. Right? And that's it. That's the full reduction. So reduction is in time exponential in order n over k. Okay? And the size of the graph is also n. Write this, and size of the graph n capital N is also this. Right? Because it's basically k times exponential n over k. And now, if you just have a couple of minutes to quietly think over it, it should be obvious that if I can pick one vertex from each, right? So I will be counting what is the largest fraction of things. So first of all, if it is 3 colorable, I can pick a proper 3 coloring, just take its restrictions to each VI, and I'll get a full k clique because there won't be any inconsistency. So 3 colorability will imply that there is a multicolored k clique here. The other direction is also not hard. So if every 3 coloring miscolors an epsilon fraction of edges, then you can say that any k vertices you pick here must miscolor, must also have some constant fraction of things miscolor. Okay, and maybe that requires the graph is bounded degree, which you can assume, but that's the case. And that shows that this problem is unlikely to have an n to the little o of k algorithm, because the original one required 2 to the n time, and this capital N is 2 to the n over k. So basically this shows that param 2 CSP, so gap ETH implies param 2 CSP needs n to the omega k time. It's actually much stronger than ruling out FPT. So in particular, it doesn't have FPT. And by the way, that's also true for our reduction. So we actually get some, I think in the paper as written, it is some n to the log k or something. But I think actually there is a simplification which I would present if I had time, which actually gets n to the log k. It's a simpler and also gets better bound. So we get something, but it is weaker, but we get n to the log k. Okay, is this clear roughly? So I thought I'll mention this because at least you see one concrete reduction, and it's a very simple reduction. This idea of taking these variables and making it into k blocks of equal size, this is very common in fine-grained hardness and so on. For example, there is this edit distance n square. This is a famous paper showing edit distance requires n square time unless Seth is false, and that also does this some. Basically, you take n variable sat, and then you make two parts, n over 2 variables, and you take all satisfying assignments to both. And of course, you do much more complicated things. But really, you get the hardness by saying, if you have something better than capital N square, where capital N is 2 to the n over 2 there, then the original problem will have something better than 2 to the n, which is not possible. So this idea of reduction based on exponential sized objects is very common.
When is this true?
Oh, this one, this particular one?
The gap increasing place.
Page maybe 15, 16. It's there in a couple of papers, yeah. And yeah, so it's not that old, but it's also very, it's a simple reduction. So I think it probably was also known in the circles. But I think people were shying away from it because it's a very strong assumption. And again, the key thing here is that we already had a gap in the assumption. So it was easy you just have to preserve the gap. You don't have to create a gap. Okay? Whereas we have to, if you work from ETH, you have to create a gap. All right, so that's all I want to say. So maybe in the last 20, 30 minutes, if I can borrow a little bit of time beyond 12:30, I'll say a little bit about the proof. Okay, to do the proof, I actually want to review a little bit of the PCP theorem ingredients, okay? And this will be a little bit fast thing to PCPs, but it's really meant as a glimpse. I don't expect you to follow the thing. So it's a little bit of a little tutorial on recap of classical PCP. In the classical world, it's a PCP which is very inefficient. It's what you use at the inner level, this Hadamard-based thing. So it doesn't, you need more things to prove the classical PCP. But here, it turns out this is the only thing you need. Okay. So again, you can forget about parameterized for a while, and then we'll talk about this NP-hard problem, which is basically a system of quadratic equations over F2. Okay, using very standard things, you can say if you have a bunch of variables x1 through xn, so you have variables x1 through xn, okay, and you have constraints of the form x transpose ai x equals bi. So these are the constraints. This is matrices. And the question is there an assignment of F2 values so that these are all satisfied? Okay, so this is a very classic NP-hard problem. Okay, just to write some examples, it could be x1, x2, plus x3, x4, plus x5 is 1, x1, x7, plus x. Okay, so I actually wrote this to be homogeneous. Let's actually make it homogeneous, so which also you can assume. Things like this over F2, so this is how they look. And you want to know, system of linear equations is easy. System of quadratic equations is NP-hard. Okay, so we start with this. So now we want to reduce this to a CSP-like problem, which is hard, which has a gap, where it's not only hard to satisfy, but it's hard to say even approximately satisfy, or to tell apart satisfiable instances from things which are far from satisfiable. So that's what we would like to do. And to do that, we move to this worldview of PCPs. PCPs and verifiers. There's a standard transformation between PCPs and CSPs, which maybe I won't dwell on here. So to do this, you use the PCP view of CSP. So another acronym here, this is the probabilistically checkable proof. Okay? So somehow the idea here is going to be, you take a proof checking view in the sense that suppose somebody wants to convince you that this system is satisfiable. There's a natural, it's in NP, so they can write down the NP witness. What's the NP witness? Just the Xi's. And you can, of course, check that all these equations are satisfied. But now, suppose, but to do that, you have to read the entire proof, x1 through xn. You have to read n variables. So the question is, can you do this? Can you check the system is quadic, is satisfiable with order 1 queries into a proof? Proof or witness. It's a witness, but you're going to be lazy and you're only going to query it in constant places. But of course, if you do this, you cannot expect to. So the nice thing with NP problems is that if this is not satisfiable, no proof anyone gives you will accept. You will reject it with certainty. But now because you're doing a sloppy check, there is a chance you will reject because you're only looking at a small part. So there is basically this X, and you encode it into this PCP proof pi. And now there is a verifier, which is randomized. What it's going to do is that it's going to just query this proof in, let's say, 4 places, read these random, chosen according to some clever distribution, and based on the values of the 4 bits it reads, it will accept or not. Okay? And now the property you would want is that if this instance is satisfiable, you can just take a satisfying assignment, encode it in this PCP view, and everything it will always accept. But if X is not, if there is no satisfying assignment, then no proof you write will work with high confidence. Okay? So maybe I'll just say this. So let's call this instance psi. So just what does the PCP guarantee give you? It gives you completeness and soundness. Completeness means that if psi is satisfiable, implies there exists pi that verifier V accepts with probability 1. And the soundness will say that if psi is not satisfiable, then for all pi, no matter what devious proof you might create, V accepts with probability at most, I don't know, some point, some 1 minus epsilon, for some epsilon greater than 0. As always, there exists an epsilon greater than 0, such that. And if you work it out, you'll get some decent value. Let's say 0.9 if you want. It accepts with probability at most 0.9. So this is what you would like. So this is what the PCP theorem gives you. Now, how you go from this to CSPs, I'll just say one sentence, because you probably have seen it in some form before, and it'll just jog your memory. You think of the variables, the locations of pi as variables. And here, let's say everything is thing. This proof is also over F2. So it's a proof of bits. So I have n bits, but I'll maybe encode it into n to the 100 bits. My proof blows up, but it becomes easier to check. Okay? And here, you think of the locations of pi as the variables, and every check the verifier makes is going to be a constraint. And that constraint will stipulate that the values those bits take should satisfy the verifier, which is now just relation. It's a higher rarity relation, but as I said, it really doesn't matter. Even if you make 1,000 queries, you can bring it back down to 2. But now the proof won't be Boolean, it will be a bigger alphabet. Okay, that's the connection. So you can immediately go from this to a CSP. But this view is nicer because now you can think a little bit more operationally. Right? You can think about the verification, what the proof should contain, and so on. All right, so, okay, I'm a little lower on time than I thought, which is okay. Okay, so now, okay, I'll just say what the one of the PCP proofs is going to be, and then I will say a little bit about how we port that. Okay? So here is a classic Hadamard code-based PCP. Sometimes also called the Walsh-Hadamard code. Okay? So what is the Hadamard code thing? So let's call this the Walsh-Hadamard code. So it's WH of x. So what is WH of x? If this is an n-bit string, so WH is going to, this is going to be a 2 to the n-bit string. So what it's going to do is that, so this is WH of x. It's a long string, much longer. From n bits, you have gone to 2 to the n bits. And at any particular location y, WHX of x at location y is simply going to be x dot y over F2. And then y, and because there are 2 to the n strings, these are indexed. Y is going to be in F2 to the n. So this is a string indexed by n-bit strings. Okay, it's a little bit confusing. It's a string indexed by n-bit strings, so the string itself is 2 to the n bits long. It's a very long, redundant encoding. But the key thing here is, the advantage with this is that any linear function you want of your x, you can get it with one query. If you want to know what the x dot y is, just go and look at it there. It's there for you. So you basically blow up this proof enormously. Now note that this is a very bad thing to do in the regular NP hardness world, because you're making n bits to 2 to the, this is an exponential time reduction. So this is really bad, but in the parameterized world, but it's still useful because you use it at some level where the parameters have become small enough. But in the parameterized world, there are only k variables. So you'll have this n becomes k and k becomes n, right? That swap thing. So you can blow up things by 2 to the k, it's not a problem. So this is something you can actually work with freely. Okay, but there is a problem. The alphabet is big, I'll come to that. But this is what you basically take. So the proof here is actually going to be, so the PCP proof, this pi will be the Welch-Hadamard code of x. So this is what pi looks like. And it's going to be the Welch-Hadamard code of x, actually x tensor x. Because you want all quadratic functions, xi, xj. So note that a quadratic function is just linear in x tensor x. Right? Because this, you can write it as A inner product x transpose as a matrix inner product. Or if you want tensors, you could just say that this is really, yeah. And you can equate this with an n square.
PCP n cube one, where you look at 3 sat, but you need 3
Three things. But you don't need, this one saves you n cubed to n square because you just work with quadratic equations. But it's the same thing, yeah. So this is also sometimes called the quadratic function code, because you tell me what the value of any quadratic function is at this point. Okay. So this basically will just, suppose you have, so here you will have some matrix A, which is Aij, and this entry will tell me summation Aij xi xj. Okay. And why do you need that? Well, because I need to access this at some high level. So this is what the proof should look like. Okay. And then the PCP essentially will do the following. I mean, it's not too important for, I don't think I'll get into that level of detail. So I'll just say what the PCP will do. See, note that the PCP must check one of these conditions. It has to check all these conditions. Now, a very cool fact, which gets you in the door first, is that how are you going to check all these constraints? That seems like you have to require, the note that a single one of these you can get with one query. If I want this, I just go to the A location of AI location of this quadratic part, I get it back, and then I just have to check if it is BI or not. Okay? Now, there is the issue that the prover may be devious. We'll come to that. But suppose there was an honest proof, I can do it with one query. But you're supposed to check all of these things with good confidence. So the first one trick you do is that you take a random linear combination of these equations. And the beauty is that even if one of them is violated, a random linear combination will be violated with probability half. And this is just because if you have a non-zero vector and I inner product it with a random vector, it will be 1 or 0 equally likely. So straight off the bat, I can take a random linear combination. So now I just have to check x transpose summation Ri Ai x equals summation Ri Bi. Now this is a bit, and this is also a quadratic function. So I can now go to this location in that proof and just check it. This all seems too good to be true. I just made one query, right? And of course, it's still not that easy because in the soundness, it has to work for any proof. And of course, there is no reason that pi must look like the Hadamard code of x and x tensor x at all. It can be whatever it wants.
quadratic test or something.
Right, so you need to check that the proof given looks like this, and if not, you should straight away reject. So that's what you really do. So for the key to the soundness is something called linearity testing, a very classic thing. How do you test if some function is linear? Because that's what really this is. If you think of this as the truth table of a function, you're really checking that it's the linear function which at f of y gives you x dot y. Okay, that's what this you're checking. And now you might have seen this Blum-Luby-Rubenfeld test. How do you test if a function is linear? Pick r and s at random and say, is f of r plus s equals f of r plus f of s. So you check that for random r and s. That's 3 queries. So you do that here. You can also do this here to check that it's linear in this quadratic space. But that alone is not enough. You actually want it to be a quadratic function code of this x. So, because this is just a general n square linear function. And for that, you can do a sort of something called a projection test, or you can basically take 2 entries here and take their product that should equal the entry here, just because it's quadratic. Okay, and again, I'm not giving the details, but these are not very standard in textbooks and so on. So you do this. So you check each one of them is linear, and you make a consistency check, and then you get some confidence that your proof kind of looks like this in most places. And then you do this, and then you're reasonably sure that you get the correct value, and you're in business. Okay? So the whole thing is really just like a couple of pages, like of analysis. Okay? And you can do this, and this is good. Okay. So that proves the exponential size PCP in the classical NP completeness world. So what are we going to do with this here? So why don't we do this here? So on the one hand, I said something is good because here n becomes k, so I can afford exponential blow up. So maybe I can just do this and I'll be done, right? But obviously, it's not that easy. So the reason is, so back to the parameterized world. So in the last, so maybe I'll take another 10 minutes or so to say a little bit about what we do in the parameterized setting. So what do we do? So our hope is to really use that. But what we're going to do, so on the one hand, so if I have k bits, f2 to the k, that gets blown to 2 to the k bits. That's something we can afford. It seems good. But this is not quite correct because we don't really have f2 to the k, we have sigma to the k. So recall, what is the parameterized CSP? I think you have k variables, and sigma is n. And you want to know, is there an assignment which satisfies some constraints, which you can assume of some form. So you can try to do the PCS, but then there's a version of the Hadamard code also over bigger fields. You can make sigma to be a field, that's not a problem. And you can take linear functions over that field. But now, this one will have f to the k symbols. Okay, so maybe sigma is f large finite field. But instead of 2 to the k, now the length of the code is f to the k. And that you cannot do because f is n. So you can't just use the Hadamard code directly. Okay? So how are we going to get around this? And perhaps there are a few things which all combine together quite nicely in getting us a result. But perhaps the main conceptual thing is this point, which is that we are going to find a form of CSP which is hard under ETH, for which we can do this Hadamard thing. Okay? So our sort of maybe key contribution is a form of ETH hardness. I'm going to be a little loose here, but it should be clear what it means. It's the ETH hardness of deciding, or exactly deciding, of parameterized vector 2 CSP. And again, no gap here. So this is just to decide if there's, exact vector 2 CSP. Okay, and I'll just tell you what this problem is, and then basically close out. And that it'll also give you a little glimpse of why then we are more or less in business. Honestly, once you sort of really understand the form of this, and you know the PCP machinery, you can work out the PCP. Okay. So I would say this one, and even this one is not that hard to prove, but really conceiving of this form is probably the main contribution in some sense. So what is a vector CSP? So the trouble here was that the sigma was, so this variable was taking a value in this big field. But now we are going to imagine the variable being a vector. So it's actually going to be, so let me actually call this f tilde just to distinguish with what I'm going to do. So now this xi is must take value in f to the d. So d is this. It's going to be a vector of length d over f. Okay, and now the point is f will be some constant, fixed constant. So I can now play these games. And of course, then something has to give because the alphabet is something has to grow. But then d will be log n. Okay? So I'm going to make my domain have this sort of vector structure. That's hence the name vector 2 CSP. And now every variable, there are k variables, each of them looks like this. And now somehow my constraints will be very nice with respect to these components. In a general 2 CSP, I can have whatever constraint I want between, so this is just the value I have to give, right? So, but in general, you can have an arbitrary relation on f to the d. But now my constraints are going to have some nice structure, okay? And that's will be conducive to this. So what is a constraint structure? So let me just draw this here, shrink it a little bit. So there are k variables. Each of them is supposed to take values in this. Now I need to tell you what the constraint structure are. Two kinds of constraints. So the first type is what is called a parallel constraint. So instead of the constraint, in general, the constraint can take this entire vector, look at them, and decide whether that pair is in the relation or not. But in a parallel thing, it's very nice. It will basically just look at the corresponding ith components like this and check that each one of them is in some relation under over just f.
And then combine them all into another relation?
No, so this will just be one relation. Maybe I'll write it down formally. So a general higher relation, r tilde of two vectors, maybe I'll call the vectors u and v. So these are supposed to be values in f to the d. So this is really going to be and of I going from 1 to d of some r ui vi.
Just the and?
Yeah, just the and. And r is just a relation over the small field. So, and you can have that between every pair or some pairs and not have between some pairs and all those things. Okay, that is one. You can have such a constraint between some pairs. So why is this sort of good? Because now if you look at this whole picture with just the parallel constraints, it's as if you have just constraints over f in parallel. The different components, coordinates don't interact at all. So in particular, you can just do, and at one component level, you have some crazy CSP. But that you can test using the Hadamard based one. And it's not a problem because the field size is small. Okay, so if I could draw better, so maybe.
The proofs have to be together consistent.
Yeah, I think you're coming to exactly the, yeah, very good. But I think it's actually, in this case, it's not really an issue. So let me just draw a little bit of what the parallel part alone looks like. Right, so you might have this constraint, right? And you might have are there other colors? And the constraints between different things can be different if needed. So maybe actually all white. So you can have another constraint like this. And then maybe you can have a constraint like this. But if you look at it in a particular layer, if I just look at the first component, so you just have x1, x2, xk, the first component, there is just some CSP between them, composed of these different relations. And I can write down a Hadamard proof for that. And now you're right that now I can write the proof for each one of these separately. And there is no consistency issue because there is no interaction between these layers. So everything works. But of course, this is a bit silly because this problem is very easy in FPT. because the whole instance just breaks up into these D components. For each one you can solve it. And note that for each one of them, the brute force algorithm is f to the k, which is just 2 to the k. So sure, you can give a PCP for it, but it's much more easier than that. You can actually decide it yourself.
Second kind of constraint.
See, the second kind of constraint will now cause some interactions between the different components, but in a very controlled way, which is also friendly to Hadamard code. Okay, and you can sort of imagine what that would be. Okay, so is that roughly clear? I'm just giving you a high-level idea. And really, honestly, yeah, so this part, if you know the standard PCP, there is nothing more to do. It's just done. You can check these things by just the standard PCP. Okay, but now the other part is these linear constraints. And what are these linear constraints going to be? In general, you're giving me a vector here and a vector here. I will just check that some linear map to these things. So suppose you have an edge E between xi, let me call it between u and v. Always the notation is a bit, let me just use xi, xj. Between xi and xj. So you will basically say that the value you give to this, so there should be some matrix AE such that, so this will be the constraint. Sorry for writing so low here. You'll basically just apply some linear map to this vector and apply some linear map to this vector and say that they're equal. That's what I call a linear constraint. And actually in our thing, the linear map will actually be even simpler. So maybe I'll just save that. We actually achieved this in our thing. The linear map will simply say that some components, some matching is equal. It doesn't even have to be a perfect matching. And it can leave some coordinates. And that's, of course, a linear constraint where these AE is just a coordinate projection map.
That is just from the encoding of sigma into the vectors.
Yeah, it's
The same label occurs, it must be the.
Yeah, it's some sort of consistency check. Yeah. So you'll basically do this thing where you'll duplicate variables and so on, and then you'll have to check that that is consistent. So, if, for example, if you make many copies of this, then you want to check the different parts are equal. So it kind of comes from that. Because the thing you need to do that is that here you have this parallel structure. So you might have some crooked constraints, but you can do permute this part to make everything parallel here. So this part looks nice. But in doing that, you have to make some consistency check with a copy. Okay. Yeah, it's really just nothing too difficult. It just you have to be very careful with the design. So
the other constraints also happen to be linear constraints, but they are like more crisscross.
More crisscross. So we write linear just because it's enough for us to design the PCP. But as I said, the linear constraint is actually just checking x1. The first coordinate here is the 14th coordinate here. The second coordinate here is the third coordinate. No constraint on the third and fourth. The fifth coordinate is the seventh coordinate. So it's really just a matching, a crooked matching. So crooked matching equality. So that's the other constraint we get. And now, of course, you can't treat all the layers separately. And in fact, we prove that this CSP is not parameterized. So what do I mean by ETH hardness? We prove that if this has an FPT algorithm for decision, exact decision, then you get a sub-exponential algorithm for 3-set. And so this is a hard enough problem to start with, and then we build a PCP for this. Okay, so I'm almost 10 minutes over time, so I'll close here by saying, as I said, the parallel part is really no sweat. We just do the Hadamard thing verbatim, nothing to worry about. For the linear part, the Hadamard is all about linearity, so you should smell that this should not be that difficult to achieve, and indeed it is not. So, but maybe the one thing I'll maybe mention is that what is the code we use? We use something called the parallel Welsh Hadamard code. But that's really something very simple, which is that if I have a vector, so what do I mean by this is that, so you have x1 through xk, and they are all getting vectors, right? The Hadamard code will take the Hadamard code of all of them. The parallel one will take just the first components and take its Hadamard code. Take the second one, take its Hadamard code, and so on and so forth, and just stack them together. So it'll basically give you a Hadamard code of the same length, but now each position will be a vector of length d. So it's really just applying the Hadamard code in parallel. Just apply it to the first row of the exercise, second row of the exercise, third row of the exercise, and then stack them all together, and that's your new proof. And once again, the proof length is small because this is only size f to the k. But the alphabet is big because each of these is like in f to the d. And d is like log n, so this is n. So it's a short proof over a big alphabet, which is what you want in the parameterized sense. And that's the code we use instead of the Hadamard code, just the parallel version of this. And then the nice thing is that for this parallel version, once you have access to the parallel version, we are able to test the linear checks also quite nicely. Okay, so I think, was there anything else I wanted to say? I think that's pretty much it. Okay, so maybe just to conclude, some open questions is obviously to prove W1 not equals FPT implies PIH. And one good thing is that if you're able to prove that this problem is W1 hard, then you're done. Because we have essentially given, we have reduced this problem to gap parameterized 2CSP, or we have given a PCP for it. Unfortunately, we can only prove this problem is hard under ETH. Can you prove that some such vector 2CSP is W1 hard? Then you will be immediately done. Maybe that is possible. And of course, the other alternative is to think of some other approaches to give the reduction.
So instead of ETH hardness, you could also have said if k click requires n to the omega k.
Yeah, okay, that may not be because it's still, that's a downstream thing, right? This is, because ETH implies that. Yeah, so it's, yeah, cannot go back, but yeah. But it's probably some specific assumption. I don't know if there any specific assumption like that implies ETH, but so that's one question. And of course, there are many other questions you can ask. So this only gets you some soundness, some rho less than 1. You can ask, can you tell if it is satisfiable versus only square root k of the constraints are satisfiable? Can you get such strong hardness results? I mean, that this approach just almost has no chance of working there. Okay, I think good time to stop. Any questions? Yeah. Yeah, don't be shy.
Is there any hope of proving that ETH implies gap ETH?
Oh,
Or that's like too strong?
that is, yeah, that will be amazing. Seems very strong. In some sense, that is sort of like asking whether you have linear size PCPs. Yeah, which maybe is not. I mean, now that you have linear length, locally testable codes and so on, maybe that's possible. Yeah, in fact, I should have also said that there were papers which said that if you have linear size PCPs, so the PCP I showed you was of course very bad. It blew up n bits to 2 to the n bits, but the traditional PCP theorem blew up n bits to poly n bits, and that was subsequently improved in a sequence of works to n poly log n, which is like the state of the art. But you can ask whether you can blow n bits to 100 n bits and have a PCP. That is still open. And if you had that, that essentially implies, that says that ETH implies gap ETH basically. So that's one avenue. So yeah, that's definitely possible, and that would be kind of nice because, actually it would be nice because gap ETH has many more downstream implications which our approach, PIH, does not. So there are still many things we know only under gap ETH, not under ETH. So if you prove ETH implies gap ETH, you just finish off that whole field, right? So you get all of those. So that will be really nice. Yeah, so which is again linear length PCPs. It's possible, I think. Yeah. The other cool result, one result is that gap ETH has this thing that I think it's gap ETH with any gap implies gap ETH with perfect completeness. This is one nice result by Mitali, Bafna, and Nikhil Vyas a few years ago in CCC. So that's kind of, I don't think something like that is known in the PCP world, in the black box thing. So what do I mean is, if you cannot tell 99% satisfiable from 98% satisfiable, that implies gap ETH. You can make the 99% 100%. which is to say that there are certain things you can do in the exponential time world which we don't have analogs of in the poly time world.
For things like AM, they can do it. Make it one-sided.
Right, right. For AM, we can make it, yeah, exactly, like these old results.
This consequence is stronger than PAH.
This consequence is stronger than PAH. And I think, as I said, what we get is that ETH implies, at least what is written in the paper, param 2CSP needs n, where n I made this new n. I think square root log k, I think, which is also stronger than not having FPT. But it's conceivable that, I mean, any proof you give is going to give you something like this, at least if you work with ETH type things. If you give traditional W1 hardness type thing without any concrete assumption, then you won't get any bounds like this. Right? Thank you.